So this is my Lab 3 microscopic view of DC and RC circuits. So I'm going to have 6 slides. The first slide is obviously the title. This is the agenda slide. Slide 3 is going to be circuit setup and observations. Fourth slide is going to be theoretical model. The fifth slide is going to be the model and observation. The sixth slide is going to be the what if and key takeaways. So for the circuit setup, we had to use two 1.5 volt batteries, two resistors which are both 47 ohms and 100 ohms respectively, 2 ammeters, wires to connect everything, with a 1F capacitor and the 2 light bulbs. So at least for the observations for the first set of the first model that we had to build was a series circuit, and there wasn't really much to look into except that obviously the voltage around the circuit stays zero, or the change in voltage adds up to 0 because KVL. And at least for this, but the second part is the RC circuit, and this contained the light bulbs and the capacitor. And what we saw was when we first connected the battery, the light bulb lights up very quickly because the current is extremely high. But then the capacitor starts to build current and build charge, so the bulb starts to dim, and then the capacitor is fully charged, so the bulb then has no light. But then when it's disconnected, when we disconnected the capacitor from the battery, we saw that the bulb lights up due to the stored charge in the capacitor. So the theoretical model that we used is the one right there for the voltage, and R is going to be equal to the resistance, C is capacitance, RC is time constraint. And from this equation, we can get RC, which is basically how fast the capacitor loses voltage when disconnecting. And yeah, pretty much it loses voltage extremely fast at the start, and then it starts to decay a bit. The assumptions that we use, what we used is the ideal battery, ideal resistor, ideal capacitor, and a negligible wire resistance. So basically, although the experiment worked, there were some slight errors clearly due to not having ideal resistors and bulbs. And basically, for at least the battery and the wires, usually resistance changes as they heat up. So bad clips and pretty much wires is going to be resistive, so it's going to mess up some of the calculations. And for the what if, we have if we charge a capacitor with no resistance, basically with our equation V equals IR, if we do solve for I, we will get V over R, and that means if there is no resistance, well, that's just basically a limit going to 0, and that's pretty much, that defies reality because all components will have resistance. And what we would see is the ammeter would rapidly go up, but it's not instantaneous because there has to be some kind of current, resistance. And the key takeaways for this is real circuits, outside of just equations and models, just from pure theory, deviate because of non-ideal components. And we can see that simple circuits, such as the ones that we built in lab, they can show energy conservation throughout the circuit, as well as exponential graphs based on time. And that's it. Thank you.